In this video, we're going to go over section 5.2 from our textbook, which is on integration by substitution. So first, we want to recall our chain rule here. So remember, if we want to take the derivative of a composition of functions like this, that's the same as taking the derivative of our outside function, evaluated at our inside function, and multiplying it by the derivative of our inside function. If we recognize an integrand as a chain rule form here, we can easily find an antiderivative and its indefinite integral. So we're going to take the indefinite integral of this derivative here, which we found by using the chain rule. We're going to get that it's just equal to the composition of functions, this guy here. So let's look at an example here. If we're interested in finding the indefinite integral of this guy here, we can notice that the integrand appears to be in our chain rule form of e to some function g of x multiplied by the derivative of g of x here. This is because if we were to take the derivative of e to the x cubed minus 1, we're just going to get exactly this here, right? We're going to take the derivative of our outside function evaluated at the inside function, so that'll just be e to the x cubed minus 1. Then we need to multiply this by the derivative of our inside function, which is going to be 3x squared. This means that if we want to take the indefinite integral of this guy here, it's just going to be equal to this original composition of functions that we have here. So we saw that in this arbitrary example here. Now, if we were to look at this indefinite integral here, we see that it's missing the constant factor of 3 here. So it's not going to be in exactly this form because the derivative of our inside function, x cubed minus 1, needs to have that 3 out in front. It'll be 3x squared. So, because a constant factor can be moved across an integral sign, what we can do is rewrite this guy. So we'll introduce the constant factor of 3 at the same time, multiply by 1 over 3, and move the 1 over 3 factor outside the integral sign. Right? So if we're essentially multiplying this guy by 1 over 3 times 3, so that's 3 over 3. So we're just multiplying this guy by a factor of 1. So we're not actually changing this integral here. So what we mean is we're multiplying by this factor of 1 here, and then we're pulling 1/3 out, so that we're left with this guy here. And so we can then see that this applies. We'll do the same thing that we do here, and we just have this 1/3 term hanging out front. All right. So something else to be careful with though is that a constant factor can be moved across an integral sign like this here, how we pulled the 1/3 out, but a variable cannot. So we wouldn't be able to do this if we were missing a variable factor of x. All right, so here are some general indefinite integral formulas here. So for example, if we want to take the integral of some function to the power n times its derivative, it would be equal to this guy here plus some constant c, okay? And so on here. So essentially what we're doing in these instances is that we are undoing the chain rule. Okay, so let's look at an example of just that. What we want to do is take the integral of this function here, and we see that it's going to be equal to this inside function here to the power n plus 1 over n plus 1 here, because our n is equal to 10, plus some constant c. Okay? So in this case, our f of x function is going to be 3x plus 4, and our derivative is equal to 3. And we're using this property here. And we know we can check this guy, because if we want to take the derivative of this, we should end up with what we're trying to integrate in the first place. All right. Next, we want to look at the definition of differentials. So if y is equal to f of x defines a differentiable function, then the differential x is going to be of the independent variable, and the differential dy is of the dependent variable y. So dy is going to be f prime of x dx. Okay? And we can think of this because if we had a function y is equal to f of x, and we want to find the derivative of y with respect to x, it would be equal to this here. And then solving for dy, we can multiply by dx on both sides, and so we get f prime of x times dx. So let's look at some examples of this. For a here, we're given our function is x cubed, and we want to find dy. So we know y is equal to x cubed. And so what we're going to do is find dy dx, which we know is going to be the derivative of y with respect to x. So it's going to be 3x squared. And then we want to find dy. So we'll do so by multiplying by dx on both sides. So we get dy is equal to 3x squared dx. Similarly, for b here, we want to find du, given u is equal to ln of 2 plus x squared. So we're going to take the derivative of u with respect to x, and here we're going to use our chain rule. So we're going to take the derivative of this evaluated at our inside function. So that'll be 1 over 2 plus x squared, and then we're going to multiply it by the derivative of our inside function, which is going to be 2x. Then multiplying both sides by x, we're going to get that du is equal to 2x over 2 plus x squared times dx. And lastly, we have the function v here is equal to e to the negative 5t. And we want to find dv. So we're going to take the derivative of v with respect to t here. We're again going to use the chain rule, so it's going to be the derivative of this guy evaluated at our inside function. Our inside function is minus 5t. So the derivative of our outside function is just going to be e to the minus 5t, and then we need to multiply by the derivative of our inside function, which is just going to be minus 5. Then multiplying by dt on both sides of this guy, we're going to get dv is equal to minus 5 e to the minus 5t times dt. All right. Now, in the next example here, this example demonstrates our method of substitution, which we'll be going over in this video, and I'm going to be calling that method of substitution U substitution. So, we want to integrate this guy here by substitution. So, suppose if u were to be equal to this function here, x squared minus 3x plus 7, notice that if we wanted to take the derivative of that with respect to x, this would be equal to 2x minus 3, which in turn, du is going to be equal to 2x minus 3 times dx if we're to multiply by dx on both sides. Notice then that this u here is equal to this guy, and du here is equal to this guy here, 2x minus 3 times dx. So what we can do is rewrite this guy with x squared minus 3x plus 7 to the 4th power times 2x minus 3 dx. Should have parentheses on this guy too. So we're going to rewrite this guy using the fact that u is equal to this and du is equal to this. So we're going to take the integral of u to the power 4 times du. So now what we're doing here is just integrating u to the 4th power. So this is going to be u to the 5th over 5 plus some constant c. And then remember we said u is equal to this, so what we'll do is we'll plug u back into this guy. So we'll get 1 over 5 times x squared minus 3x plus 7 to the 5th power plus some constant c. And we can check that this is the case, because if we were to take the derivative of this guy here, we would find that it would be equal to what we're trying to integrate here. All right. Now, this substitution method is also called the change of variable method, since u replaces the variable x in this process. Right? But I'll just be referring it to as u substitution. So here are some more indefinite integral formulas here. We're trying to integrate u to the power n. We're going to get u to the power n plus 1 over n plus 1 plus some constant c. This one we should be familiar with, as well as this one here. So the same properties we've seen before. And these formulas are going to be valid if u is an independent variable or if u is a function of another variable. And du is going to be our differential of u with respect to that variable. So here is a little procedure for using integration by substitution. So we're going to select a substitution that appears to simplify our integrand, so what we're trying to integrate. Then we're going to express the integrand entirely in terms of u and du, and evaluate this new integral. So let's look at these two examples here. For a here, we have this here. Sorry that these screenshots are a little blurry. All right, so we want to integrate this. And so notice we have this composition of functions here. I'm going to let u be equal to 2x cubed minus 3. This means that du dx, so taking the derivative of this guy with respect to x, is going to be 6x squared. So this tells me that du is going to be, actually don't think I'm enough room there, du is going to be equal to 6x squared times dx. We multiply dx on both sides. So what we can do is rewrite this guy as the integral of u to the 4 times du. Since 6x squared dx is equal to du. So this whole thing is going to be equal to du. Alright, so now we can just integrate this using this property here. So this is going to be u to the 5th power over 5 plus some constant c. And then plugging in our value for u, we're going to get 1 over 5 times 2x cubed minus 3 to the 5th power plus our constant c. All right, looking at part B now, looking at the integral of e to the 5w times 5. What we can do here is we see again this composition of functions. We're going to let u be equal to this 5w here. Then this means the derivative of u with respect to w is going to be equal to 5, and therefore du is going to be equal to 5 dw. So this means we can rewrite this as e to the u, since u is equal to 5w, and then 5 times dw is equal to du. So we can evaluate this using this property here. So the integral of this guy is just going to be e to the u plus c. And then we're going to plug our value for u back in. So we have e to the 5w plus c. All right, so now we're going to look at some cases where we're going to have to do a little more work to use u substitution, because to use u substitution, we need the integrand to be expressed entirely in terms of u and du. So let's look at these examples here. We'll start with A. We're looking at the integral of e to the minus 3x. And so what we'll do here is we again have this composition of functions, e to the power minus 3x. So we're going to let u be equal to our inside function minus 3x. In this case, du over dx, the derivative of that with respect to x is going to be minus 3. So this tells us that du is going to be minus 3 dx. So let's try to rewrite this guy. We're going to have the integral of e to the u, and then du here is going to be equal to minus 3 dx, but we just have dx here. So what we can do is solve for dx. So we'll divide by 3 on both sides. Divide by negative 3. So what we get is du over minus 3 is equal to dx. So we'll rewrite this guy by plugging in du minus 3 for dx here. Alright, and remember we can pull a constant outside of our integral here, and this constant is minus 1 over 3. So we end up with this here. And then this is minus. Alright, now we can evaluate the integral like normal. So this is going to be e to the u plus c. And then we'll plug in our value for u back in. So e to the minus 3x plus c. Alright, let's look at another example here. We're going to look at b. We have x over x squared minus 9. What we're going to do here is we're going to let u be equal to x squared minus 9. So then du over dx is equal to 2x. So we can rewrite this. We have this u here, and we have that du is equal to 2x dx. But here we just have x times dx. We don't have this factor of 2 here. So what we'll do is we'll divide by 2 on both sides. And so this tells us that du over 2 is equal to x dx. And that's exactly what we have here. We have 1 over x squared minus 9 times x dx. So we can rewrite this as 1 over u, since u is equal to x squared minus 9, times du over 2, since x dx is equal to du over 2. Again, pulling this constant out, we have the integral of 1 over u. And then looking at, I believe, this property up here, we see that the integral of this guy is going to be equal to ln of the absolute value of u plus some constant c. And then plugging u back into this guy, we'll get ln of x squared minus 9 plus c. Alright, and the last example we'll look at is c here. So we're going to integrate 5t squared times t cubed plus 4 to the negative 2. And so again, we have this composition of functions. This t cubed plus 4 is our inside function, so we're going to let that be equal to u. This tells us du over dx is then going to be 3t squared. So then du is going to be 3t squared dx. Alright. So we know we can write this as u to the minus 2, right? Since this is equal to u to the minus 2 here. And then we're left with 5t squared dx, right? Because this guy can actually be rewritten as this here, right? This is the same thing. But du is equal to 3t squared dx, not 5t squared dx. So what we can do is rewrite this guy by multiplying by a factor of 5/3 on both sides. When doing so, we'll get that these 3's cancel here, and we're left with 5t² dx. So this tells us that this 5t² dx is equal to 5/3 times du. All right. We can pull this 5/3 out since it's a constant. Now integrating u to the minus 2, this will just be, n is our minus 2, so this will be n plus 1, so minus 2 plus 1, so we'll get minus 1. So u to the minus 1 over minus 1 plus some constant c. So this will be minus 5/3 times 1 over u plus c, rewriting that with positive exponents. And then plugging in our value for u, we will get t³ plus 4, and then we still have this constant c. Okay, so this is our value for this guy. The last thing we're going to look at is this application problem here. We're told that the marginal price at a supply level of X tubes per week for a certain brand of toothpaste is given by this function here. We want to find the price supply equation if the supplier is willing to supply 100 tubes per week at this price here. So we want to find the price supply equation, which is P of X here. And we're given the marginal price, which is the derivative of P of X here. So what we'll do is we'll use the fact that the integral and the derivative undo each other. So if we want to find P of X given the derivative of P of X, we're going to take the integral of the derivative. Okay. So plugging in our value for P prime of X, we have this here. And we can pull out the 0.001 since it's a constant. And what we'll do here is we have this composition of functions here. So we'll let u be equal to our inside function. So this tells us that du dx is equal to 0.01. And therefore du is equal to 0.01 dx. So we're going to have 0.01 times the integral of e to the u, and then we have this dx term here. But notice that we have du is equal to 0.01 dx, right? So what we're going to do is rewrite this. So we're going to get dx alone. And we can do so by multiplying by 100 on both sides. So we'll get 100 du is equal to dx. So plugging this information into our integrand, we have this here. So we can pull out this factor of 100 as well, and just take the integral of e to the u here. So we'll get 0.001 times 100 is going to be 0.1. And we know the integral of e to the u is going to be e to the u plus some constant c. Okay. Then plugging in our value for u back into our function here, we have 0.01x plus some constant c. Okay. So this is our price supply equation. Okay. Now the question asked us to find this equation if the supplier is willing to supply 100 tubes per week at this price here. So what we need to do is actually, we're not done with this guy yet. What we need to do is use that information to find this value for c here. So we know that when x is equal to 100, plugging this in here, this is going to be equal to 3.65. all right, because we're looking at the price supply equation, and that is what happens if the supplier is willing to supply 100 tubes per week at that price. All right, so doing so, we'll get that e to the power 1 plus c is equal to this here. And then solving for c, we'll get c is equal to 3.38. And so this tells us our price supply equation is given by this here. All right. And then the last question, it asks us how many tubes would the supplier be willing to supply at this price here. So we're going to solve for x when the price is 3.98. So first we'll subtract 3.38 from both sides. So we'll get 0.6 is equal to 0.1 e to the 0.01 x. Then dividing by 0.1, we'll get 6 is equal to e to the 0.01 x. And then taking ln on both sides, since ln and e are inverses of each other, we'll get ln of 6 is equal to 0.01 x. And finally, solving for x by dividing by 0.01, we get this is roughly equal to 179.18. So this tells us we're looking at roughly 180 tubes is how many tubes the supplier would be willing to supply at this price here. Alright, so that'll be it for this video.